Hey everyone, so today we're going to look at some free body diagrams and forces. What we're going to do is I'm going to show you some examples of situations where free body diagrams occur. And when I tell you to pause the video, I'd like you to pause the video and sketch out what you think the free body diagram looks like. And then we'll unpause the video and we can compare our answers and see if they match up. Okay? Okay, so the first example is someone sat down on a flat surface. What are the, he's in equilibrium, he's not moving. What are the two forces acting on him? Can you sketch the free body diagram? So pause the video and sketch the free body diagram. Okay, did you get that? Right, so the free body diagram, there's two forces acting on the object, okay? There is weight pulling the person down and pulling the object down, but there's also a second force, a reaction force, that's pushing up from the table. The table is literally pushing up on the object, and it is pushing with the same magnitude of force that is equal to weight, but in the completely opposite direction. And so that's why the object is not moving, it's in equilibrium. Okay, so a little bit more of a complicated example in this case. What I've got here is basically like a little seesaw thing where there's a pivot and it's able to move around the pivot. And I'm just going to add some masses to either end of the Lego. So if I add one there, it drops down. If I add one there, and it's pretty much balanced. It's almost perfectly balanced. So we've got two masses there, and I just want you to think, what is the free body diagrams just in this area? So sketch that out. You can sketch a diagram of this. What is the free body diagram just for this area? Okay, pause the video, have a go. Okay, did you get that? Right, so in this case, we've got two forces pulling down and they're equally distributed. So we've got two weights pulling down here like this. So if we were to draw it to scale, the arrows would be about half the size of the reaction force. And in this case, the reaction force is happening here. So the reaction force should be twice the length of the arrows on this side here. Okay. Okay, so we've got a little bit more of a complicated example here. We've got a slope, we've got someone on skis, and there are three forces acting on the person right now. Alright, pause the video and sketch what you think those three forces are. Okay, did you get that? So in this case, we have the first force going down is weight that's pulling down on the slope, pulling down the skier, and it's going down perpendicular, straight down basically. Then we have a reaction force, like the example of someone sitting on the chair, but in this case, the reaction force is actually going up at right angles to the slope itself, so up at 90 degrees to the slope. So now we've got some unbalanced forces because we've got a force that's going up, but it's also going slightly down as well, slightly to the left because of the direction of the arrow. So that means there is one third and final force, and that force is frictional force that's going against the ski, so going up along the slope, going up along the length of the slope. And what we find is that those three arrows of forces, if we drew them to scale, they would form a right angled triangle. And because they form a right angled triangle, it basically means that both the horizontal forces and the vertical forces cancel each other out. So there's no overall force until I increase the angle and I've reduced the reaction force gets slightly bigger and cancel, and we have unbalanced forces. But we're going to look at that in a little bit later. Okay, so for this one I've had to really move everything around a little bit, but what we've got here is we've got a car on the top, you can just see over there, car on the top right, we've got a pulley in the top left of the table, and we've got a mass on the bottom. Okay, so sketch the free body diagram for this. Pause the video, I'll get back to you in a second. Okay, so let's look at the car to start off with. So I'm just going to zoom up and look at the car to start off with, and we'll zoom in on the car. Okay, so on the car, we actually have two forces acting on it, okay? Vertically, we have weight going down and we have the reaction force going up. But we also have two forces acting on it horizontally. We have a pull, a tension, created by the weight hanging down, and we also have friction in the opposite direction. But they are completely cancelled out, so the tension in the string, if the pulley was perfectly frictionless, would be equal to the weight of the bricks that are pulling down on the pulley. So the tension should be equal to the weights over there. Okay, so we're going to say that the tension here, so when we draw a free body diagram, tension we could say equals the mass of the bricks times the gravitational field strength, and that will be the same size to the friction on the car that going in the opposite direction. And then we have weight and we have reaction force. If I add weight to the pulley, if I add weight to the mass below the pulley, we'll create an unbalanced force where eventually the weight will be greater than the friction between the tyres and the wood, and we'll get it moving. So let's try that. Okay, so I've actually added a little bit more weight. We're going to let it go. Okay, and we're going to leave it there. Next couple of videos I'm going to post are going to be using the same sort of setup. We're going to be looking at free body diagrams again, but we're doing some calculations based on it. We're going to be looking at the coefficient of friction, both static friction and kinetic friction, and we're also going to be looking at Newton's laws of motion. Take care, everyone.